Hey, what's up, guys? Today we're going to be doing invert binary tree from our LeetCode 75 level 2 questions. So the question states, I'm not sharing my screen. Okay, I am not. All right, perfect. I'm sharing my screen. So the question states that basically this is the tree and we need to just invert it. Everything needs to be inverted. So 7 child 6 and 9 should be replaced. So this should become 9 6. This 2 and 7 go there with its all the children. Now keep in mind the way the connection works in these type of tree is we create our own class. Binary tree doesn't really exist. We create this class and you can consider it as like a linked list kind of stuff because they're like pointers, right? So if I just change 7 to go to 2 and the way I change is I put this whole node here, replace it with this, then this automatically is going to come with 7 because they're linked to it, right? So how it's going to work is we can go inside 2, then go inside 1, and then check. This is null, and then say this is also null, then just return, same, check, null, null, and then just say, okay, now I just want to replace 3 and 1. So I just replace 3 and 1. So this becomes 3, this becomes 1. Now once I go to the left side, I want to go to the right side. I go to the right side. I do the same process here. I replace 9 and 6, right? So this returns to finally to 4. Now 4 will finally say, okay, I just want to make this now 7 by the same process of these nodes and this 2. And as I said, this would whole be carried since it's kind of like a linked list you can consider to over here. And this whole thing would be carried to the right hand side. So basically what we are saying is do a DFS to the node leftmost as much as you can unless you find a null. Then do the same thing for the right hand side as well. And once you are done, finally, you can just swap the values. So let's see. On a code, we are saying a base case is if it's null, return none. That's the easiest base case. Then we are saying our left node L is just going to be equal to invert tree root dot left. So what happens is first time with 4, it's going to go 2. Then on 2, it's going to run it again 1. And 1, it's going to run again till it finds null. Then it's going to return null to it. So our left actually for the first time is null. Now for the right, again, right child is also null here. So our right also becomes null, right? So let's just see how it works. So once we got the L value, it said, I want to go to right would say return root equal to null, it returns. Root dot left is just going to be right, this one, the one we defined over here. So we are just saying root dot left is equal to null, root dot right equal to null. And then we return the root. So once we return it, we are back here, right? That means what returned to me here was a 1, because root here was 1, right? Now I'm going to run this condition, right? Go to 3, then I'm going to run left. Left is going to say null. Then it's going to return it here. Then right will also be going to be null. And it's also going to return similar process. Null is just getting swapped. Easy peasy. And then we're going to return here. So left here is actually 1. Right here is actually 3. Now we're just going to swap it. So left would actually now become right. So root dot left is now 3 and root dot right just becomes 1. And then we say return the root. So return the root, that means left here is nothing but 2. Right, we want to go again in the tree. So we say invert tree again, recursion, go in. Once we go in, it's going to come here and run the tree node L equal to invert tree root dot left. Similar process comes here, it swaps null null, it swaps null null, gets returned, these two get swapped, then it returns here, the right just becomes 7, and then it just swaps both of them. So that's how this whole question works. I hope it made clear to you how to do this question. And the next one we probably shall be doing is balanced binary tree. That seems like a good one to base this solution for that one. And I'll see you guys in next video.